Now, we worked on systems of equations yesterday, but some of the systems that you guys looked at were gnarly. Why were they gnarly? Because there were polynomial equations in there, there were quadratics in there were circle equations in there. Today, you're only going to look at linear equations, which you'll like a lot more because there's not, a bunch of factoring to do and squaring and all that stuff. It's just linear equations. And so, more practice with linear equations, and with it comes what I'm going to talk about right here. Here we have two lines right here, two linear equations. They cross at one point. Whenever they have a different slope, they'll cross at one point. Here we have two parallel lines. They don't cross at all. This one has no solution. This one has one solution. Why does it have one solution? Because it crosses at one point. Here, they don't cross at any point. Now here, you can't see the second line because the lines are on top of each other. They are the same line. Whenever you get the same line, then you have many, or infinitely many solutions. Okay? Now, this one's called an independent system. Whoa, it just changed like that. This one's called an independent system because it has one solution. And I remember it by thinking like, what do you think of when you think of independent? I think of one dude standing alone, like, I'm independent. That's one, right? So that's how I remember independent solution. Inconsistent, well, that just kind of makes sense. If I don't get a solution, that's just, it's inconsistent. I don't know why that makes sense, but some of you guys might be able to agree that it does. This one right here, this is called a dependent system. This one's probably the hardest one to remember. When I think about it, I call it dependent because it's dependent upon both of the slopes and the y-intercepts being the same in order to get it. Okay? All right. So we have one solution, no solution, many solutions. So let's look at an example. So here's our first one, and we can solve this using elimination. And this one's already set up for us. It's nice and pretty. The reason why it's set up is if I add these two functions together, you see how the x's are on top of each other, the y's are on top of each other, the equal signs are on top of each other, and the constants are on top of each other. If they're all on top of each other like that, then it's ready. And not only that, so we get 8x, we get 0 y's. That's what we want. If you get a 0, then that variable gets eliminated. Because we have opposite numbers here, they add to get 0, so it gets eliminated, which is why I think it's called elimination. I've also heard it called different things. Instead of elimination, I've heard linear combinations or adding or subtracting equations. It's just, they call them different things. Elimination, I think, is the most common. So here I would divide both sides by 8. I get x equals, I simplify that, that's going to be 3 over 2. So that's your x. 3 over 2. What's my y? Remember, we always need to have a point for a solution because it's a system of equations. So I'm going to take the x, I'm going to plug it over into one of these x's. It doesn't matter which one. I think I'm going to just choose the first one. So we have 3 times x plus 2y equals 4. I plug in the answer, 3 over 2. I multiply it. I get 9 over 2 plus 2y equals 4. Subtract 9 over 2 from both sides. And in fact, I'm not going to write 9 over 2 anymore. I'm going to write 4 and 1/2 because it's easier to see that way. I have 2y equals, what's 4 minus 4?
0.
Yeah, it's 0. And then I have to subtract 1/2 still, so I get negative 1/2. How do I get rid of this 2? You divide it by 2 because that's the inverse operation. Now if I divide this by 2, that's the same as taking the 1/2 and multiplying it by the reciprocal of 2, which equals negative 1 over 4. There's your answer for the first one. Okay, now you sometimes might get these not ready, like everything's not lined up. Like this, the same problem, it could say 3x plus 2y equals 4, and the other one could say 5x equals 8 plus 2y. Do you see the difference between this one and this one? Okay, are they different though? They're not different. Why? Because what you would do here on this bottom one is you would get this y, this 2y over here to go to the other side, and you would subtract 2y. So it would say 5x minus 2y. That's what it says right here, 5x minus 2y. So these are the same systems. This one just looks like it's complicated because not everything's set up and ready to go. So here's the second example I want to show you. It's actually example 3 in the book, but it's everything's lined up. We have the x's, the y's, the equals, and the constants lined up. But if I were to go and add this, will one of the variables get eliminated? No, one of the variables will not get eliminated. So we have to manipulate them a little bit. Now there is a property that says that we can multiply both sides by the same number, both sides of the equation. We can multiply both sides of this by the same number and the equation is the same. So now what you have to do right now is you have to choose which variable do you want to eliminate. Do you want to eliminate the x's or the y's? It doesn't matter.
X.
All right, guys, come on. Which one? X. Okay. I heard x's, and I don't want to do y's because Natalie wants to do y's. Okay. Natalie. Okay. So if we want to eliminate the x's, what's the common multiple for 5 and 2? 10. So one of these has to be positive 10. One of these has to be negative 10. It doesn't matter which one. So what do you guys want to multiply the top one by? Dose. And what do you guys want to multiply the bottom one by? Negative 5. Very good, because we want a negative 10. So on the top, we multiply everything by 2. So we get 10x plus 6y equals 18. On the bottom, we get negative 10x plus 20y equals negative 70. Okay, double check my multiplication. Guys, this is where everybody makes their mistakes.
Why did you do that?
Why did I multiply them?
Yeah.
Because check it out. Will the x's get eliminated?
Yeah.
Yes, that's why I did it.
But you can still do it the other way, right?
Let's finish this bad boy. So the x's get eliminated. So let's see. I add those together. Let's see. Those equal 0. I get 26 y's, and on the right side, let's see, that's going to be 62, 52. Negative 52. Oh, perfect. Isn't that negative 2?
Yes.
Faux show. All right, so negative 2 is my y. Let's just find our x, and we're done. You can plug this y into any of the y's that you guys have up here to find your answer. I'm going to do this one just because it looks really clean. So we have 2x minus 4, and we're going to plug in the negative 2 equals 14. So I do my thing. I get positive 8. I subtract 8 from both sides. I get 6 equals 2x. So x equals 3. That's your answer. Here's example 5 out of your book. I just took a picture of it. Here's the equation, or the system of equations. Now they're going to solve it, and they're using elimination. And so they multiply the top one by 2 to get this. Then they combine them. They add the 2 and the negative 2, they cancel out. They add the negative 4 and the 4, and they cancel out. So I had 0 equals 7. All the variables cancel out. That means it's going to be no solution or many solutions. Now how can you tell which one it is? Well, this one is not true. You see? 0 equals 7 is not true. So therefore, no solution for this one. If you guys go down and look at the example 6, you'll see the other end of it. So they do the same thing, they solve it, but this time they get 0 equals 0. This is a true statement. So therefore, the solution is infinitely, yeah, Lee, is that E supposed to be there? Many solutions, okay? That's your answer for this one. So if the variables get eliminated, then you know it's going to be infinitely many, or it's going to be no solution. And you can tell by whether or not the statement is true. All right, that's it.